Splendid. Okay, Matti, thanks very much.
Yes, thanks you. Thanks for the invitation. It's really a pleasure to give this talk, and it's a joint work with my PhD student Pietari Laitinen. And indeed, we try to make the adaptive MCMC theory a bit more accessible to tell the nice story about that. Hopefully nice to everybody. So I have to start somewhere, so that's going to be MCMC, which you probably all know. Then what's tuning of MCMC, and finally adaptation of MCMC before we get to the actual business of checking the theory. So this slide is mostly fixing notation because you probably all know MCMC. So basically there are two things: pi, which will be the probability density of interest on some state space X, which is usually like subset of RD, but could be basically anything. We don't care so much about the geometry of the space in this talk. And we try to estimate this expectation where we are looking at expected values over this probability distribution pi of some test function phi. And phi is real valued to make the theory easier. But basically, if we can make things valid for one phi, then usually it works for a number of other phis too. So I will be looking at this example during the talk, which is basically the well-known sort of Gaussian target, which is twisted to be a banana-shaped. And that's a good sort of example for MCMC. And basically, these are the contours here. And what do we do with MCMC is that we basically draw samples X, which sort of will be roughly samples from the distribution pi, but at the end, when we have a lot of samples, this average will approximate well the quantity of interest, pi of phi. And many interesting MCMC transitions, like the random walk metropolis, which was the example in the previous slide, they have parameters. So in the random walk, the parameter is usually either the covariance matrix of the jumps which are proposed, or the perturbations, or the size. Even simpler, you can just look at the case where covariance is just theta squared times the identity matrix. So basically, theta is just the size of typical size of jumps proportional to that. And if we look at what happens to the random walk metropolis with different choices of theta or the scale, we see that sort of too small value here, 0.11, leads to this sort of diffusive behavior and not very efficient sampling, because it takes ages to go from one tail to the other in the target distribution, and that leads to strong or large serial correlation and bad estimates. Here on the right, the scale is 11, which means actually that we are proposing samples from a very large, with very large typical jump size, and it means that most of them are actually rejected. So we only see the accepted ones here. And that's why there are so few of them, because this chain is sort of sticky, a lot of rejections. And in the middle, we sort of have the sweet spot theta, which means that the chain is sort of accepting enough, but moving fast enough too, so that you get efficient sampling. And there are sort of theoretical works that actually try to formalize or give ideas or rules of thumb based on theory for how should you choose the parameter in the random walk metropolis. And this is actually a series of works beginning from the late 90s. And roughly, there are two branches of rules. One is that the proposal covariance should be proportional to the target distribution covariance matrix, sigma pi. And then you basically scale down by 1 over d, where d is dimension, and there's a magic number from the theory. And the other rule of thumb is that the accept rate should be something like 0.234, at least in higher dimensions. And these kind of rules give you basically possibility to try whether some choice of S actually produces something like this. You can basically use the trial runs and try to learn these iteratively or tune these iteratively. And what adaptive MCMC does is that basically this is where it all started, actually, tuning a random walk metropolis sampler. You make this automatic so that the sampler is self-learning while it's sampling. So it's sort of online learning of the parameters during sampling. And there are a number of algorithms, and I've added references to 3 different algorithms. And without going to the details, just if we look at how they perform on this same example, they all seem to be doing pretty good job in sampling from these. And now for the talk, I will be focusing on perhaps the simplest but still useful algorithm, the what I call adaptive scaling metropolis. This is simplest because you only have one real valued parameter which you tune, which is the scale or the step size. And this is the algorithm. So, okay, it's a lot of equations, but actually I can explain a little bit. So basically, if this bit which I highlighted, if you put theta there, a positive theta, then the first 2 steps are just the proposal, forming the proposal, and then accept reject step of a random walk metropolis sampler. And the highlighted bit is indeed just the step size theta, or jump size parameter. And the adaptive algorithm, in the adaptive algorithm, you don't have a fixed value here, but you change it on the fly. And basically, this is the rule how you change it. It's iterative. And basically, the intuition is easy here because this is the accept rate, so the probability that you accept the proposal yk plus 1. If the acceptance probability is bigger than the desired one, 0.234, then you actually make your scale bigger. Next time you make bigger jumps than on average, and vice versa. So basically, this is sort of intuitive, actually, that if you decrease the step size, the accept probability increases. So, and why I like this algorithm a lot is that it's very simple to implement. And there's essentially only one parameter to tune, and it's this step size sequence here, which is gamma k. And so my example here is that the step size is something like k to a negative power. And you can do something else, but what's important is that you make the step size go to 0, because then you actually can get a valid algorithm. I'm going to get back to that a bit later. But if you would freeze the step size to some positive constant value, then actually you end up with a biased algorithm. So the X case won't sort of sample from the right distribution even asymptotically. So this is sort of the first bit where theory is needed, or theory is necessary to understand why this has to go to 0 so that you can ensure the validity. Well, when adaptive MCMC is valid then? to get to that, you have to somehow formalize the business, what's going on. We try to be rather general. And okay, if you don't know what filtrations are, or if you are not familiar with them, it might seem bad, but I just tell what this means. So basically it means that so SK is your parameter which you adapt, and XK is the MCMC chain, which you actually try to sample. So given the values up to K of these guys, the next X must come from this Markov transition. That's basically the only thing in the condition. And usually you have exactly this, but then you might have an update rule for S based on the previous values of the chain, and then maybe the previous value of S or whatever. But this is quite general, actually, this condition, but not too technical, hopefully. So if we look at our example, the adaptive scaling metropolis, and if we put to the general framework, then these two steps actually are the xk plus 1 sampled from psk. So Markov transition P with parameter sk and previous point xk. So that's all. So basically the transition probability is just random walk metropolis with e to the sk scale. Proposal step size. And then the adaptation bit where we update the S is just, it's iterative, and here actually the update rule also depends on the proposed point yk plus 1, in addition to the accepted point or the actual Markov chain or the actual samples xk which we produce. Okay, so that's rather simple. So somehow you have these two things in an adaptive MCMC when you actually implement one. And what do I mean by the algorithm being valid? So somehow, because if we are interested in approximating this quantity by the average, it's sensible to say that, okay, we want consistency. So we want actually this average to converge to pi of phi. So this is what we want. That's the minimal requirement for adaptive MCMC somehow to be valid. And now, to get to the business of showing the validity, I'm going to go for a bit more specific case. So now we start to have assumptions. So the test function phi will be bounded in what follows. And we will assume this condition here, which is called in the literature actually simultaneous uniform ergodicity. And so it means basically that the iterates of the transition kernel, k iterates of the transition probability p with parameter s, will be close to pi uniformly, regardless of the point x and the parameter s. And there's even this sort of geometric decay rate for the upper bound. And if you are more familiar with Markov chain mixing times, this is also the same thing as saying that the mixing time of all of these possible MCMC kernels, the mixing time will be upper bounded uniformly. So regardless of the parameter s. So this is quite a strong assumption, but it makes the following things easier. And then I will return to discuss a little bit where you can generalize if you want to. Okay, so this will be, I think, the most technical slide in the talk. And so take a deep breath. So what's the theoretical tool that we will be using? It's a so-called solution of Poisson's equation. And it's this thing here. So basically, we have our test function phi fixed. And we have this infinite sum here, k from 0 to infinity, and denote that by, that's a function gs. And this is abstract. So in practice, you usually don't have access to the function. This is purely a theoretical business here. And actually, it's even a question in general whether this is well defined, but actually in this nice setting that we are in, it will be well defined. So the sum converges pointwise. And when this sum converges and everything is good, then if you sort of apply the Markov transition to this function gs, you can imagine that the ps, it's a linear operator. So the Markov transition is a linear operator on functions. It goes, by linearity, it goes to the individual sum terms. What happens to the first term is that basically you just add one of the ps's there, so you will increase the power by 1. So there will be sort of k plus 1. And the constant won't be changed at all. So basically, when you do this, you see that you get exactly the same sum, but without the 0th term. And the term 0, so where k equals 0, this thing here is actually an identity operator. So it sort of vanishes, and we see that if we subtract the sum from 0 to infinity from the sum from 1 to infinity, we only get the 0th term. So this holds, this identity here. And this identity actually, which is boxed, is the so-called Poisson's equation. So this is sort of interesting, will be key for the developments later, but this might be something that takes a little bit of time to absorb. What's nice is that actually under our setting, where phi is bounded and where the chains are simultaneously uniformly ergodic, we can actually bound the supremum norm, or the maximum value, absolute value of the function gs, by basically bounding the individual terms in the sum. And if you know the variational characterization of the total variation distance, you can actually follow the thing, and you have an inequality for individual terms, and then you end up with this upper bound here, which only involves the supremum norm of phi, and then the constant c and rho from the simultaneous uniform ergodicity. So, okay, so G is abstract, but in the nice setting, it's still uniformly bounded functions. So that's sort of nice. We know something about G.
Matti, could I just recommend maybe you say for a moment how P acts on functions, in case someone hasn't seen that?
Yes. So basically, this thing is the same thing as looking at the conditional expectation of the function value in one step of the Markov chain. So that's the same thing as doing this P of G. And of course, you can represent that by an integral too. Yes, that's a good question. And also the iterates are similarly then looking at the k steps of the Markov chain and looking at the conditional expectation of the k steps. Yep. Good. Yes. So then we go to the sort of the main central thing, how we can go to proving the law of large numbers, or consistency for adaptive MCMC, or MCMC actually. It comes also as a side product. So this is a very nice decomposition, and it's from an earlier work. So it's not my invention, but I very much like it. So the first thing is that, okay, so this is the sum we have to control. So basically, we have to make sure that 1 over n multiplied by this sum goes to 0. So the sum is less than order n, basically. The first thing what we do is that we use this identity, which is boxed here. So because the sum terms will be like this, and we can replace them by any of these with any s. So the s is totally free, and I just pick sk here. And that really is just an identity. Well, that doesn't lead directly to anything so interesting, perhaps, but once you do this thing, so you add and subtract a few times, so you add and subtract the blue things and you add and subtract the red things, then you end up with something more interesting. And basically, the last bit is nice because if you look at this term, it has all the indices k minus 1. And this term here it's exactly the same, but with indices k everywhere. So this sum here will be telescoping. So you only are left with the 0th and the nth term. So that's sorted because the g's and the pg's are bounded. So actually that's order 1, doesn't increase in n at all. Then if we look at the first term here, if you look at the blue term, and if you start to think about what's the conditional expectation of the blue term up to the information up to time k minus 1, you notice that it is exactly the red guy, which means that basically this term will be a martingale. And even better, the terms in the sum or the martingale differences are bounded. So this is very well behaved martingale, and we know a lot about them. So basically, it's almost like they were independent random variables like that. So that's also good. And we are left with this middle term here. And basically, this is where the adaptation sort of can destroy things, or can disturb everything. So first, maybe just to note that if sk is same as sk minus 1, so if we didn't have adaptation at all, this term would be identically 0. Actually, that's the simple MCMC case, and this is a simple way actually to prove the law of large numbers for simple MCMC. But once we have the adaptation, there may be something happening here, and we have to sort of ensure that this term doesn't grow too fast, basically. And how can we do that? So we sort of cooked up this sufficient condition for making this go to 0. And in words, it just is that these kernels, these consecutive kernels with where we do pick the s, but somehow if the kernels are often enough, close enough to each other, then we are actually in good shape. So we call this thing waning adaptation. I don't know if it's a good name, but there were some other words or some other names which were allocated to other things already. So that's what we came up with. And what's the condition? So basically, it assumes that the total variation differences of the kernel starting from the same points x are bounded by some random variables dk. And if the average of those random variables goes to 0, in probability or almost surely we call the adaptation one waning weakly or strongly. And basically the key thing is that if we have this, then it does guarantee that this term here will be small enough. So if we divide this by n, remember that's what we are doing at the end. We are dividing by n each term here. If we divide by n, it goes to 0, and therefore we really do get this consistency for adaptive MCMC. And there are some more details, which I'm not going to go through now, but you have to sort of believe me for now. But somehow the essential idea is that you are looking at the sum form of the g's, and you are sort of bounding the individual sum terms, but it involves a little bit of more calculation, which are in the paper. Well, there has been, we are not the first persons to look at the validity or convergence of adaptive MCMC averages. So there are many other conditions, sufficient conditions for making sure that adaptive MCMC is good. One of them, which is quite well known, is so-called diminishing adaptation by Gareth and Jeff. So with the same notation as in the waning adaptation, decays are bound in the total variation differences. They call the adaptation diminishing if the decays go to 0 in probability. Okay. And it's actually quite easy to see that if that happens, then we will have also waning adaptation. So somehow this is a bit more general than the diminishing adaptation, or at least it accommodates the diminishing adaptation condition. And then basically we can recover the weak law of large numbers, which they proved, Gareth and Jeff proved by a coupling technique in their paper with the same assumptions. One sort of very common class of adaptive MCMC algorithms is so-called stochastic gradient type or Robbins-Monroe adaptive MCMC algorithms. And there are a couple of references here. There are a lot more in the literature than these. So the adaptation looks exactly like so. Actually, as you may recognize, the adaptive scaling algorithm is one of these. So the updates on S are iterative, and there is that step size gamma, and then there are random variables hk appearing in the update. And there is a longer story to this, why it's relevant, but somehow this can be sort of a stochastic gradient. So somehow, if we are in stationarity, so if xk would come from pi, then the expected values of hk are usually sort of some function h of the sk, the adaptive parameter. And if we sort of would be in a pure stochastic gradient, this function would be a negative gradient of a loss function, which we want to minimize to optimize things. But it can be a bit more general, where the h is not the negative gradient, but pointing to the same direction. That's sufficient for making things work. But anyway, so I don't want to get too deep to the why this works. There's a very good reference of the review of Christoph and Johannes about this, which I recommend. Anyway, so if we look at the example, the adaptive scaling metropolis, this is stochastic gradient type. So there the random variables hk plus 1 are of this form. So the accept probability minus 0.234. And those are actually, within this range quite easily, you can see, because this is within 0, 1. And if I calculate correctly, then you get that range. Which means that the difference of the consecutive S's, so if we look at this, the difference of the consecutive S's is just this bit. So then the difference of the consecutive S's will be less than a constant times gamma. So we know that the SKs are getting closer and closer when you iterate. And then there's a technical result from the literature that for a random walk metropolis algorithm, actually, if the scaling parameters or the covariance matrices are close to each other, then we actually have the total variations also upper bounded by the difference of the scaling parameters or the covariance matrices. There are a little bit more technicalities, so you actually have to make sure that the scaling or the covariance matrix eigenvalues are both lower bounded and upper bounded to make this work. And this constant, this sort of Lipschitz constant L depends on those lower and upper bounds on there. But that's a bit of a technical thing there, but very important in practice too. So now, if we assume that the SKs are sort of contained within some range, then we actually can choose DKs to be something like this. Now, the total variations will be upper bounded by a constant times gamma, and as long as we have the gammas which are decaying, then we are good. So we get one waning adaptation and a result. So this picture is actually showing how SKs evolve in one of the adaptive scaling metropolis. So this sort of, the changes get smaller and smaller over time. And it actually converges in the end, but not going to get to that in more detail. And yes, so if we are in a, if we have something else than the adaptive scaling metropolis, but still of the stochastic gradient flavor, the same kind of story usually works. So these increments, HK will be sort of order 1, maybe stochastically order 1 or something a bit different, but somehow morally anyway, order 1. And the differences are order gamma K. So as long as these things go to 0, you are sort of fine. But we do need some sort of continuity for this mapping of the parameters which are mapped to the kernels. So as I told, the previous condition here was sort of Lipschitz continuity, and you can relax that. You can look at something like maybe Hölder or even other types of continuity. And they often work. There are many samplers that actually are nicely continuous in this sense. But unfortunately, some samplers might not be continuous in this sense at all, or at least not in a Lipschitz or Hölder sense. But instead, we might have to maybe change the metric somehow, that we measure the differences, or something else. But anyway, it can be the case that you don't have continuity at all, or verifying the continuity is super hard in practice if you have a complicated algorithm. So this is sort of a problem for this setting, or can be a problem. So more recently, Cyril, Chris, and Gareth suggested actually a new way to do adaptive MCMC, which they call increasingly rarely, or AIR, a very lightweight way of doing adaptation. Anyway, so what's the idea? It's very simple, actually. So the idea is that you only allow adaptation or changing the parameter in at some pre-specified times for j. you have some pre-specified times, increasing times, where you are allowed to change the parameter, and otherwise you keep the parameters fixed. And what's the good thing about this is that actually if you keep the parameters fixed, then the decay variables, before they were looking at the total variations of the difference of the consecutive kernels, those will be trivially zero. So that's sort of the magic here. And I think they were focusing on these kind of sequences where tau k's are like k to power 1 plus beta, which means basically that these adapt times behave like k to the beta for some beta parameter. So basically the distance or the time, the adaptations will happen increasingly rarely, because time tau k, it takes k to the beta time to adapt again. So basically that's the thing. And why this is so interesting, I think, and an interesting idea, is that, well, the authors were talking about computational benefits. That's one thing. So if your adaptation is costly, so if you have to do sort of expensive optimization business or something when you are changing the parameter sk or learning, then it may be much better to actually do it quite infrequently. So that's one thing. But I really like the other bit also. This is maybe, well, at least theoretically, this is very interesting. And basically, you sort of get rid of the continuity assumption almost like entirely. And yeah, this is interesting for theory, I think. And then you can, okay, in that paper, they had already conditions that ensure the validity of air approach to adaptive MCMC, of course. But if we look at this, well, our framework with waning adaptation, then we can ask the question, when is air waning? And basically, you can parameterize this thing by two things. So you can look at these change events. So basically, the change events are just that you actually change the parameter sk, and tau k, which are the times when change event happens. Two different ways, but they are like equivalent, different characterizations of the same business. So what's nice about this is that it's actually very easy. I think they were focusing on fixed, like pre-specified times, but you can imagine of stopping time business here. So you can even sort of have adaptive times when you adapt if you want to. The theory is not substantially more complicated, actually. So there are fairly transparent conditions which ensure that you still are one waning. So yeah, not going to the details of these, or not going to show you examples of these. There are some in the paper if you are interested. But anyway, so quite general conditions. Okay, and then somehow maybe having some reflections or something like that about these things. Well, the first thing is actually a sort of a question. So the waning adaptation was a new condition that tries to accommodate different kinds of adaptation. At least it covers the air and the stochastic gradient type adaptations, can cover those. So then the one question is that, is it necessary to get validity? And well, the answer is no. You don't need waning adaptation for validity. And there are some details, but I want to sort of, maybe the important business here is that if you assume the S case to be just entirely independent of X case, so if you, for instance, you have a different process that makes the tuning of SKs, and then you are sampling it. Conditional of them, you are doing the sampling XKs. Then actually these functions here in the AN term, the GKs or the GSs, they are zero mean. So it's sort of intuitive that averages of zero mean functions, like zero mean under stationarity, if XKs would be from pi. So averages of zero mean functions, it's plausible that they go to zero. And indeed that happens under certain assumptions at least. And why I sort of like this example or this thing is that to me it sort of suggests that okay, maybe SKs being totally independent of XKs is not so interesting, but if SKs are nearly independent of XKs, maybe the perturbation of the adaptation caused by the adaptation is small too. So maybe if you have approximately the weak dependence, maybe you have small perturbations too. So somehow, to me, this suggests that actually these sort of inter-chain adaptations, so where you actually run many Markov chains or many adaptive chains in parallel, which all learn from each other, that might actually be a very good idea, because you sort of, well, there is no real theory for saying this, but to me it suggests that you might be able to even say something with this thing about those things. But anyway, speculative thing. Now as I promised, I will talk a little bit about going beyond the strong assumption which we have, the simultaneous uniform ergodicity. There are sort of two directions where you can generalize. One is that you get rid of the uniform ergodicity. So roughly speaking, this is when you are doing sampling in unbounded state spaces, at least with random walk, metropolis, Mala, or HMC. Those can be geometrically ergodic in an unbounded state space, but never uniformly ergodic. So somehow this is sort of one thing. And there are already, well, the paper of Christoph and Eric from 2006 covers the geometric case already. And there are even papers on covering the polynomial or subgeometric cases. The other is sort of getting rid of the simultaneous business. So the simultaneous is that somehow all your Markov chains are equally well mixing. Roughly speaking, this means that you have to restrict your adaptation. Like in the random walk, you lower bound the eigenvalues, you upper bound the eigenvalues, you sort of fix those things and you constrain your adaptation. If you don't constrain it, a priori your covariance is maybe anything, so then you end up with sort of stability issues. And those are sort of, in certain cases, you can show that things are stable, and then you can add stabilization mechanisms too. But again, much more technicalities in the theory. Yes, and we didn't really cover the extensions for the waning adaptation. I think something like that could be useful in those contexts too, but you might have to change total variation metric to a weighted total variation if you do the geometric ergodicity, or you might even try to do something totally different, like Wasserstein contraction properties, which were discussed in a recent paper. Then one thing is that somehow I'm quite enthusiastic actually about this AIR approach to adaptive MCMC, because it sort of gives you a lot of freedom to design adaptive schemes. You don't have to care about the regularity or continuity of the Markov chains. And you could even, instead of sort of doing Robbins-Monroe stochastic gradient or stochastic approximation, you could do Adam, or you could do any other favorite optimization, because you are not sort of constrained by doing certain type of optimization. And well, they give conditions for validity, and waning adaptation also can ensure validity of air. But somehow, of course, validity or convergence, the ultimate convergence of the averages is, well, it's a start, but ideally we would like adaptation that actually helps in practice. And I think the core question for adaptive MCMC is, which is, I think, mostly unanswered by now, is that basically when or which kind of adaptation actually improves performance in a non-asymptotic way. This is a hard question, but I think this would be interesting if there would be developments. I think there's some, there has been some recent progress, at least in the non-asymptotic understanding of adaptive MCMC. So with the air adaptation, you can do non-asymptotic convergence bounds, and there was also a very recent paper on sort of lower bounds for distributional convergence of adaptive MCMC. So, well, there were upper bounds too, but I think the lower bound is interesting itself. And to somehow, okay, to wrap up. So I think adaptive MCMC is an extremely useful framework or approach, and it should be in much wider use. I think many people haven't felt good in using these algorithms because there is always a long list of technical assumptions which you have to sort of fulfill to make the method even valid. But somehow, if you go through a little bit of theory, maybe you get the confidence that, okay, like in statistics often, you get the feeling that, okay, this is good and those are the essential bits. And if you make the essential things right, then things are right at the end too, even though you wouldn't be able to actually do the precise things. Somehow you need some sort of optimization proxy to make these things work in practice, but there's a lot of room for creativity here. I think a little bit of theory could be useful if you try to do these things. So you can try to look at our paper. There are also references to other papers. So I encourage you to do a little bit of theory, and basically my message is that, okay, doing a formal verification often requires technical assumptions, but if you do a little bit of theory, maybe actually it still helps even if you are not able to do every detail to do rigorous formal verification. And of course, if you do like something like air, maybe it's easier to actually do the actual rigorous formal verification. What we suggest the weighing adaptation, it does accommodate both of these schemes, so air and stochastic gradient type or other continuous adaptation schemes. So then there's an obvious question, should we use one of these in practice? So one thing is the theory, but the other thing is the practice. So is one better than the other? Or should we actually try to use a hybrid of them? So maybe we start with continuous and then we continue with increasingly rarely, or vice versa. Who knows? Actually, there is a little bit of an advertisement here. So if you do a certain kind of hybrid, you can even make the adaptation convergent. So that's possible. And the final thing is that, which I touched earlier, is that adaptation within these parallel MCMC samplers, where you run many MCMC samplers in parallel, I think it's an underexplored area, and there could be a lot of very useful algorithms out there to find basically in that area. So yeah, that's everything. Thanks.